Look at this digital maze. When you rely on guesswork to test software, your testing only illuminates the obvious paths. That leaves dark, unexecuted logic branches where critical bugs hide. We are going to fix that by translating a raw block of code into a map, calculating its mathematical complexity, and finding the exact number of paths you need to fully test it. Grab a pen and paper or a digital drawing tool and follow along. We'll use this sample code on the left as our starting point. Moving away from intuition-based testing and adopting mathematical path mapping gives you the certainty that your software will remain stable under pressure. Step 1. We need to group lines of code that run sequentially, without any branches, into a single visual object called a node. Here on the left, we have lines 1, 2, and 3. Because they run sequentially, they combine to become a single circle on our map. Do not draw a separate node for every single line. That common trap will ruin your calculations. Next, we have to handle compound conditions, the statements containing and or operators. These branching points are called predicate nodes. They represent the exact moments where the program splits into true or false realities. Even if it's a single line of code, compound logic like if A or B must visually split into multiple predicate nodes. Accurately defining these nodes right now ensures that our final complexity calculation will be mathematically sound. Step 2. We draw arrows, known as edges, to map the actual execution flow of the program between our established nodes. Notice the multiple arrows coming out of our orange predicate nodes. Now look at the enclosed blank spaces formed by these connected edges. We call these regions. Make sure you include the most easily forgotten region, the infinite space outside the graph boundaries. That counts as your final region. By completing this geometry of nodes, edges, and regions, we have gathered the exact raw data needed to calculate our testing target. Now we solve for cyclomatic complexity, or V of G. This number gives us the mathematical upper bound of independent test cases required for this code. Look at Formula 1 on screen. Cyclomatic complexity equals the number of regions. Count your enclosed spaces plus the outside area, and you have your answer. To verify that math, use Formula 2. Edges minus nodes plus 2. Run the numbers and you get the exact same result. For a fast check, use Formula 3. Predicate nodes plus 1. Count your orange branching points, add 1, and the total matches again. Reaching an identical number across all three formulas proves the math is correct, locking in the exact target of independent paths we need to test. That target number tells us how many paths to find. The actual list of those routes through the code is called the basis set. There is a strict rule for building this list. A path must travel down at least one new edge that hasn't been used yet. Here is our first baseline path, tracing straight from the start of the program to the end. We iterate through the remaining paths by branching out into those unused edges until we hit our complexity number. Generating this basis set takes an abstract mathematical concept and turns it into a concrete, executable checklist for quality assurance. We started with a confusing, untestable block of code. Now we have a clear visual map and a verified complexity score. Running this specific basis set guarantees 100% statement coverage, ensuring every condition is tested on both its true and false sides. Take this basis set into your testing framework and construct your data inputs to force the code down those exact mapped routes. Mastering cyclomatic complexity replaces developer guesswork with mathematical certainty. Your bugs have nowhere left to hide.